We're going to cover 4 different groups of molecules now. Alkenes. Everybody say alkene. Are you all alkene today?
Yes.
That's what we like to hear.
Looks good, sir. Looks good.
Nothing escapes you, Mikhail.
Looks good, sir.
Thank you. Okay, watch what we do. We take, what are the black ones? Black ones are? Carbons. They've got 4 holes. We push in, what are these grey lines? No, these lines. Bonds. Now watch what I'm going to do. I'm going to bend this one and push it in there. And now all I need is 1 more hydrogen. Now look what we got. You see we got 2 hydrogens and double bonded carbon. So we draw it like this. Carbon, carbon, double bond, hydrogen, 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 hydrogen. Now what's the name of it? These are the enes, this is methane, ethane, propane, butane. Now let's do it. Ethene, propene, butene. Carry on. Pentene, hexene, heptene, octene. Everyone again, come on, I see some people chewing, not speaking. Methane, ethene, propene, butene, pentene, hexene, heptene, octene. So this is ethene. Now who would like to tell me? Singing. Would you tell us why we do not get methane? We go, ethene, propene, but we don't sing methane. Why, Soneli? Why do we not get Anna? We can't do a double bond unless you've got 2 hydrogens. Does that make sense? Yes. Soneli? Make sense? Okay. Sorry? Now watch what I'm going to do. We covered that pretty quick, didn't we? Now pull out a hydrogen. I pull out another hydrogen. I stick in one of these long grey ones. What are they? It's a bond. Who can tell us what type of bond? Covalent, because this is an intra or extra molecular force. This is, explain why it's intra, thank you. Cassie, why is it intra? That means inside. Okay. Outside and between. So, intra, inside you. Yeah, that bubble gum is intra you. Between you two, there's an extra, what do we call it? Interconnected conversation. Interconnected. Between you. Now watch. Do you see that? Come on guys, I'm trying to train you to be really good memory. There's method to my madness. That's why I'm not giving you notes until you can, from yourself, write a note. Then I'll give you a note, plenty. But till you've shown some effort to memorize this, I can't help you. Now look at that. What do you notice? 1, 2, 3 bonds. So this is what we call alkynes. And this is C123H. So let's go. Ethyne, propyne, butine, pentine, hexyne, octine. I think I might have got lost there. Okay, does that make sense? So what is this called? Ethyne. And then it goes all the way up to octine.
So is it hexyne?
Ethyne, propyne, butine, pentine, hexyne. Heptine, octine. Okay, are you guys remembering this? Remembering this?
Yes, sir.
Okay, now I'm going to introduce you to another concept. Look at that. Do you see how lovely and symmetrical that is? Can we say that this side is... Can we say that... Can we say that this side is positive and this side is negative? Because they're symmetrical. So why is this side going to be negative and this side positive? Can we say this side's positive and this side's negative?
Yes. Because it's
Why would it be? Because it's identical to this side. So when something is symmetrical, and do you remember what we say the ability to suck electrons is called?
Oh no, that's
What is the ability to suck electrons called? It's called... And do you remember what the electronegativity of hydrogen is? It's... And carbon is 2,5. They're more or less the same. So nothing's sucking electrons super big. Difference. Make sense?
Oh my God.
So look, if I had a molecule like oxygen, that's going to suck electrons because oxygen's got an electronegativity of 3.5. But fluorine, it's got an electronegativity of 4. The moment I add oxygen or fluorine or nitrogen, it becomes what we call a polar molecule. This is what we call a non-polar molecule. Have you ever heard of the terms polar and non-polar? Okay. Let me explain what's polar. If I took something like this, I want all of you to begin to think, how do the electrons get sucked by each atom? Who thinks, no. Honestly, it's not going to help you if you're sitting chatting and then you come to me and you say, Sir never explains this properly. Right? So, can you see where the suction of electrons is going to occur? 3.5, 2.1, 2.1, 2.1, 2.1, and we can ignore the middle, which is 2.5. So where is the electrons going to get sucked?
On the side.
They're going to get sucked to the oxygen, right? So here becomes electronegative. Delta negative. Because it is sucking the electrons away from this hydrogen in particular, this one becomes delta positive. And that we call polar, because there's now a positive and a negative section to the molecule. You can see this is not symmetrical. That helps. And it helps if it's got a non-polar oxygen molecule, the one that's got a higher electronegativity.
So oxygen won't be sucking from carbon.
It will. So, if I were to draw the covalent bond, you remember you drew it with a dot and a cross. You remember that?
Yes, sir.
It would suck the dot and the cross closer to the oxygen and closer to the, away from the hydrogen, right? So, you see, because the dots and the cross are close, this becomes very negative, this becomes very positive, or non-negative. So this, all the electrons are sucked away, so this is left positive. I want you to be able to, when you see a molecule like this, is there one section positive, one section negative? No. It sucks equally. You look at that. It sucks equally. It's not polar.
When the sucking happens, does this value is like 2.1 and 2.5, and that's decrease.
No. Stays exactly the same.
So then what does change?
Okay? Misha asked what changed. The electronegativity doesn't change. The position of the shared electrons changes.
Oh, I see.
Okay. Okay. Let's get to the next two groups. Next
So
group.
and non-polar?
They look like this.
Will non-polar occur here by ethene?
Will non-polar occur by?
No, it's fine. Here by ethene.
Is ethene polar or non-polar?
That's what I'm saying non-polar because it's symmetrical, so is that
Symmetrical non-polar.
Sir, how do you name the alkenes again?
Sorry?
Sorry.
ethene propene?
There's no methane. There's only ethene propene. Okay?
So I'm going to ask where would the polar occur in the alkenes or the alkynes?
It does not, because
Oh, so is that the one of its codes? Is that the group on its own? So the polar.
no,
Is a polar an exception? Sir?
no. What? Let me just enlighten you. Polar is like boiling point. It's a characteristic of it.
Yes, sir. I see you.
So if it's symmetrical and if it's got no high electronegative molecules, it will be what we call non-polar. Now here's the implication. Non-polar substances are petrol and fat. You know petrol and fat. Now we have paints that dissolve in petrol and fat. We call them oil-based paints because they're non-polar. Now non-polar paints dissolve in non-polar solvents. Who knows what the other type of paint we get?
Water-based.
Water-based PVA paints. Now watch
So
this.
that will be polar because that H2O, so they have the oxygen which have 3.5.
So those are non-polar, dissolves in non-polar. So Mikhail, do you see where we're going with this? If I do that for you, and you know the relevance of polar or non-polar, you can work it out from the electronegativity, right? You will know a hell of a lot about the properties of this. For example, Mikhail, and anyone, 1, 2, 3, 4 hydrogens. What is the strength of the intermolecular forces? Is it high or low?
No.
It's 4, right? If there's 4 hydrogens, so what type of bonds do they form? 4 intermolecular, not hydrogen bonds, not covalent, dispersion, otherwise known as London or van der Waals forces. So it's got a dispersion, London, van der Waals force of 1, 2, 3, 4. That's your test today, right? Yes.
So if we ethane doesn't have 3 carbons.
Ethine could have 3 bonds, but 2 carbons. Just have a look here. There's.
Oh, I see. Oh, he's a man.
Now look what I've added. It's a bit dark, and I'm colorblind, but that's a red one. We had to drill them out because these molymods were. I never knew that molymods over the decades melt, so the holes got smaller.
Yeah.
So I have to drill them out during break. I nearly drilled a hole through my hand as well during break.
So you colorblind?
I'm very colorblind.
Alright, so
Do you know colorblind people?
what color is my hair?
Well, I'm good enough to know that it's probably black or brown. Am I right? What color is it? Yeah. And your uniform, and your uniform's red. Okay, I kind of know enough. Okay.
Papers off the topic, they asked why you use substance in water with a fire underneath instead of just above a fire. Then why?
Which substance? Oh, like this practical.
Yes,
Okay.
it's off the topic, but it's just
Yeah, with that ether practical, we don't just heat it on an open flame. We put it in what is called a water bath. Because if I put it on a flame, it's going to go to any temperature. We don't know. It's all going to boil, right? It's going to go to 100 degrees. But we want it to react at 70. So I put it in a water bath where the temperature is below boiling at about 70, and it worked. So a water bath is like, if you're going to poach an egg or boil an egg, you don't want it to get to frying temperature, you want it to stay below 100. That's right.
So the stuff that we're writing the text on is alkenes.
No, the test is on basically your forces. So what are the different forces? Let's get to the next one. The next one is the aldehydes. Hang on. Aldehyde. Ketones and aldehydes. Yeah. Okay. These all end in L. Methanol, ethanol, propanol, butanol, pentanol, hexanol, heptanol, octanol. What do the aldehydes have? There's a nice song by Paul Simon called Just Call Me Al. So now we're going to call these Al. Heard that song? Just call me Al. Okay. There's that one. What is its name? It's got one carbon. Methane. L. Okay, let's go it, everybody. Methanol, ethanol, propanol, butanol, pentanol, hexanol, heptanol, octanol. Now, the important point about these is, first of all, do you notice that it's got O, which is going to make it polar or non-polar? Polar. Why? Because this is 3.5 and this is 2.5. So all the electrons are going to crowd more.
No, it says hydrogen 2.1.
Yeah, I don't use 2.1.
They're going to.
Carbon is 2.5 always.
Oh, you're talking about
Hydrogens are 2.1. Okay, so the electrons are going to crowd here, and so this side is going to become slightly negative, and it's the other side is going to become slightly positive. We call this polar. And if we got two of these molecules, we would have what we call dipole attraction. So if I built another one of these, they would stick to opposite ends of each other, and that's called dipole attraction. Everyone say dipole attraction. So we get London or dispersion, dipoles, and what's the third one? Hydrogen bond. I know one person's going to do fantastically. Fakila's going to do very well.
So can you tell me once again what is dispersion?
Okay. What are dispersion forces? Would you like to know what dispersion forces are? Is it an attractive force?
No.
If it were me, it wouldn't.
Is it an attractive force? I'm going to try and show you what it is. This is a piece of carbon paper. Has someone got a plastic ruler for me?
Really?
Anyone got a plastic ruler for me?
Yes.
I'm going to rub my hair with it, so you're going to have to not mind that.
So it's foil carbon paper.
Okay, watch this. I'm going to stop this moving. Now watch. Is there an attractive force?
No.
Do you see anything happening?
No.
Any attractive force? Nothing? Nothing happens. It doesn't work well on a day that is moist. But let's try. I'm rubbing some electrons onto this ruler. Oh, please work. Oh, great. I told you it doesn't work well on cold days. It's got to be on a day when there's not so many water molecules in the air. Okay, watch. Yeah, but it's working badly because it will normally pull violently the silver foil. There, did you see it pull a little bit? Who wants to try rubbing their own hair with a ruler and just see if maybe it'll work better? What else can we rub? Let me try a plastic pen. Okay, plastic pen. You see, this is cotton. It will come try it with your artificial fiber. You see, I'll show it to you on a day that's not so moist. Okay. Now, can we just pretend for a moment that here's my ruler. Here's my ruler. It's got extra negatives on it. And guys, you've got to listen. For some reason, when I bring the silver foil to it, the foil will normally spring towards it. Now why? Here, watch. Silver foil or aluminium foil is a sea of positive nuclei surrounded by free electrons. That's what we call a metal. Just look at this again. A sea of positive nuclei surrounded by a sea of negative electrons. Now what's going to happen when I bring this close to that? Look what happens to the electrons. They're free to move. Which side are they going to go to?
The other side.
So let me just point to which direction you think they're going to go. This ruler, we've rubbed the electrons onto it. Where will the electrons go? Here or here? Here or here? Who says to the left? Hands up. Who says to the right? Okay, democracy rules. The electrons are repelled. Now look what happens. Positive is attracted to negative. That is a London or
Dispersion.
because it's a temporary force that acts when they get close together. It only works when they get close together and it's only temporary. But does it make sense to you? Does it make sense to you, ladies? Why does this occur? Why is this pulled towards the ruler? Because we rub the electrons off onto the ruler by rubbing it. We actually left our hair slightly positive. Those negatives chase the electrons to that side of the foil, leaving the positive who can't move stuck on the side. Now negative attracts positive and pulls it. That is like dispersional reinforcement. Except what happens is we have two hydrogens. Now hydrogen is just a proton. Did you know that? With an electron. Did you know that? It's got an atomic number of 1, atomic mass of 1. The only thing that is in a hydrogen is one proton and one electron. Now watch what they do. Watch what the hydrogens do when they get close together. They synchronize their electrons like this. Now watch what happens if we synchronize our electrons. That would be there, and this one would be here. Now look what happens when they synchronize their electrons. Negative attracts positive. That negative is too far away to repel that one. That positive is kind of far away. So we've got close forces, so what's going to happen? These are going to be pulled together by dispersion, London van der Waals forces. How does it work? If the atoms come together, the hydrogens, they synchronize the orbitals. And so they make sure that this one's on the far side, this one, and what's the force? There's this electrostatic force of attraction. And that's why it gets pulled. That's a weak force. Only worth 1 kilojoule per mole. Happy, everyone? I know I'm telling you a lot, but I know that, you see, physics makes common sense. Common sense. I can tell you a whole day of common sense, and you're going to remember it because it makes common sense. Am I right or not? Is there anyone who doesn't understand this? Because I'm pouring a lot on you. Okay, so that's London or dispersion forces. Now let's get back to this. We've got an aldehyde, methanol, ethanol. This is methanol. It's got a dipole. It's got a positive and a negative side, so they can stick together with dipole forces. Do you remember the value of those dipole forces? They're stronger than van der Waals. What is their value? Not 10, that's the hydrogen bonds. What's in between 1 and 10? 5 or 4. So it's got a strength of 4. Dipole forces.
Which one is correct? So 4 or 5?
You see, it's an imprecise science. I guess if you looked it up on some sites, they'd say 4, 4.5, 5. It just depends.
So you're not wrong if you say, let's say 4.5.
I don't mind what you say, as long as you know it's like halfway between. Are you happy with that? Just one thing about the aldehydes. They polar. Will they dissolve in water? Will they dissolve in water? They've got a negative side and a positive side. The small ones will. But as they get longer, now let's get longer. Methanol, ethanol. Now notice I must keep the oxygen on the end one. Propanol. And we go all the way to octanol. C double bond O. 1, 2, 3, 4, 5, 6, 7, 8.
What's that?
Octanol.
Oh.
They're in water, they will.
You see, it's got this little bit that will join with water.
Right, it's dominated.
But it's got this whole lot that is what we call non-pola. So the longer the L's are, the more oil or petrol soluble they become, and the less water soluble they become.
More fat.
Make sense? So the short ones are water soluble, the long ones are fat soluble. And you know, I'm just going to give you one last group. The aldehydes, you know. Now look at this. The ketones. They all end in -one. Watch what they look like. -one. Now look what they've got. What's the difference between this and this? It's, what did somebody say? The double bond is at the end with the L's and in the middle with the ketones. The ketones.
What was going on for tomorrow? Because there's a lot of stuff that I didn't understand, and a lot of people, and so now we understand it. So
Well, see, that's my strategy, to go over it again so you understand.
yes, so what we do tomorrow? So we can go revise it.
No, I'll allow you to ask questions for a while, and while you can make notes, and then if you've got any more questions. Did anyone bother to watch my video on YouTube?
Yes.
Thank you. It's not that I care. I've got 80,000 views already. I don't get paid for it. I don't care if I've got 10 views because they don't pay me for it, and I just do it. And you're anyway the stars of this, so I should be paying you if I was getting money.
So some of us aren't in the physics group.
You aren't in that?
Physics group, some of us.
I know some of you got phone numbers that go 061. Are you on WhatsApp?
Yes, sir.
Are you on WhatsApp? And
Yes,
who
mine is
has-
065, but I'm not on WhatsApp.
and did you get a message from me?
No, sir.
Strange, because I've entered your numbers and for some reason it's
So
not.
we don't
I'm
have
not-
on a piece of paper.
I'm not there also, sir.
We don't have on a piece of paper. We don't have on a piece of paper.
You don't have?
We wrote out on a piece of paper. The other day we wrote the physics paper, and then
Are you talking about the practical or the paper?
so we wrote the practical, and then we told so we're not on the group, and we wrote our numbers down on a page.
All right. Now, if you did that, I need to just know who's in that group, and then when you did your results, did you give me those added to your results? Jamie?
How does that mean? So you just
You
gave us a
can't,
piece
you
of
can't just
paper.
have one page. Everyone in your group has got to write the results.
No, sir, you gave us a paper where we wrote our numbers on, and those people that were
Which number?
our phone numbers, so that you
Oh
can
yeah,
get us the
I've got that. I've got that.
So that's
Yeah. Except for one or two.
because I changed it now.
And I've got all of your parents' numbers except for about 5 or 6.
I don't think you have my parents' number.
So I'm going to just ask those who I haven't got. Just let me finish this. So this group is got a name. It's called the carbonyl group. Just say that, everybody. Carbonyl group. A double bond oxygen is called a carbonyl group. So what is the characteristic of aldehydes? The carbonyl group is on the end one. Ketones, the carbonyl group is in the middle. Let's sing the ketones. We don't get methanone. Ethanone, we don't get ethanone, because then there's only 2 carbons and it would be on the end one. So we start with propanone, butanone, pentanone, hexanone, heptanone, octanone.
Sir, but if this, even numbers, then where do you want to carry?
Well, we have ways of numbering the carbon chain. So if it's on the whichever end it's closest to is where we put it.
Sir, can you
I've done propanone. Oh, there's propanone. Yeah. As long as it's in the middle. Butanone, okay, 1, 2, 3, 4. I can put it here or here. It makes no difference. It's still on the second carbon from the end. You haven't yet got to the numbering, but we number it whichever side it's closest to. So this becomes carbon number 1, 2. If you put it here, it becomes 1, 2, carbon number 3, carbon number 4. That is for later. I am exposing you to all the things before I go into the details. So if we can sing them all, then I'm going to ask you things like, what makes an alkene? And you're all going to say, there's a double bonded carbon. If I say what makes an alkyne, you're going to say there's a triple bonded carbon. If I say to you what makes an aldehyde, you're going to say
There's a double oxygen bond at the
there's
end.
a double bonded oxygen called a carbonyl group on the end carbon. Who asked that original question? Mikhail. If I stuck it here, how would I number it?
1, 2.
1, 2. If I stuck it here, the oxygen, I would have to number it 1, 2. We always start from the closest side, numbering. Makes no difference. You can, because look, we make the molecule, we flip it around, it's the same molecule. So now you've learned 4 new groups. Okay. I'm going to ask you to make notes on today's work. If you didn't catch Thursday's work, make notes on that as well. If you got any questions, ask them. But there will be a test that lasts 10 minutes just before the end of the day on last Thursday's work and what we covered again today. I think I covered everything that's in the test today already again.
So is this test that you're going to write now?
And it's for your report, so is tomorrow, so is the following, and so is as long as we're writing little tests. The only thing I did cover was hydrogen bonds. This is, well, here's our hydrogen bond. If we did kind of cover it like this.
Let's go for that.
There is a hydrogen bond. And by the way, if we draw strokes, we will draw all the strokes. I'm lazy, I did leave some out when I told you. Sorry. But that's between hydrogen and oxygen is what we call a hydrogen bond. What's its strength?
2,1. Oh, damn. Strength.
Do you remember between O and H? So there's your 3 types of intermolecular forces. London dispersion van der Waals. It's all the same thing.
So you can just remember London.
Or dispersion, or for today van der Waals. Either will get you a mark. Now you know what? The textbooks and the examiners are so confused. They think that van der Waals have the learning. They think that dipole forces, they even in the note that I give you today, they will write that dipole are van der Waals forces, they're not. And they think that hydrogen bonds are van der Waals forces, they're not. I looked it up on the internet this morning. Van der Waals forces are these temporary ones that come from atoms synchronizing their motion, and they weak. They have a value of 1. And they temporary. Whereas that is permanent. And that is a permanent force.
So van der Waals is temporary always.
Temporary.
So when they're in sync, they are more like the same. Like when they're in sync.
When they're in sync, then they get a little force. Until they get close enough, they don't get into sync. That's why they're temporary. You see, here, that oxygen is permanently negative. It doesn't require anything, it is permanently negative. Why? Because it's got a 3.5 negative. This one is permanently negative, and that hydrogen is permanently positive because it sucks the electrons away from it. So that's permanent, therefore it's not a van der Waals force. That's permanent, it's not a van der Waals. But the notes that I'm going to give you that came from the department are going to make you say different, but they're wrong. Okay. Do your notes, get something down. Just write anything you remember. What's the topic? Alkenes, alkynes, aldehydes, and ketones.
wanted.
Okay. You've given me the original one?
Yep.
I know, I was needing the one. Okay. Right.